Samir Ruiwale is a principal engineer at Intel in Oregon. He leads manufacturing, test development, and execution for products in Intel's client portfolio. And he's been heavily involved and passionate about manufacturing strategy, execution, and standardization. And with that, Samir, the floor is all yours.
Thank you, Ira. Morning, everybody, or afternoon, evening. I would like to talk about test economics in a die disaggregated world. Some of the themes have been covered in the earlier presentations, and I'd like to give an introduction to this pending problem that is getting exposed as our industry moves more and more towards heterogeneous integration and disaggregation. So we will jump right in. Die disaggregation is the future. I think we've all seen our industries moving very rapidly towards heterogeneous integration. This has been driven by the continuous need to extend Moore's law as transistor sizes get smaller, keep approaching atomic scales. We rely on heterogeneous integration to extend Moore's law, to extend the economics of Moore's law. Putting performance IPs on cutting edge nodes, putting other standard IP blocks on older and cheaper, higher yielding nodes, and again, using smaller chiplets area-wise, which result in higher yields, lower costs. All of these things have propelled the fast rise of heterogeneous integration in our industry. And all, the very different 3D stacking methods, 2D stacking methods, advanced assembly technologies is enabling heterogeneous integration at an even faster pace. All of this has a very profound impact on the test ecosystem. It's creating a lot of high complexity, a lot of test cost, hardware and capital costs in the test space that we've never seen until now, and it's increasing exponentially. Some of the key points, and we'll get into them in the presentation, are that we have a known good strategy that's now needed to minimize package yield loss as we integrate more and more chiplets on the package. You want to make sure that each chiplet is known good die so that you don't fail at the package level, and that's very expensive because you're throwing away the substrate and you're throwing away other die on the package as well. Lots of complexity to support this strategy of known good die. Lots of test time in wafer sort to do what we call quote unquote characterized known good die, and we'll talk about why we would need that and what are the complexities associated with that. Probe cards go up. For each chiplet now, you need an individual probe card, complex technologies for these probe cards, all of this leading to added capital cost, hardware expenditure. As integration increases, the micro bumps, the pitch increases for all these micro bumps, and these pose signal integrity challenges and lead to very complex I/O methods, test methods that cause differences between wafer test and final test, and have impacts to can we test these things correctly? Can we test them to the fullest extent with wafer sort technologies, or do we have to continue doing package test? And again, add to differences, add to test time, test complexity in our test space. In addition to all of this, all of the interconnect itself between these different chiplets in a disaggregated die introduces additional cost and complexity. How do you deal with interconnect? How do you test it? Do you test it? Do you have repair methods, repair technologies that are implemented? What impact does that have for test? What impact does it have on the die area, on the die design, DFT? So there's lots of considerations that have all of these vectors that impact our test ecosystem. So let's look at some of these. So let's talk about test hardware impact. Individual chiplets drive up probe card count. That's just a basic, more chiplets you have, the more probe cards you need. And you need them typically at the same time. When you have a die disaggregated product and you have multiple die being put on the package, you're typically going to sort them together. And that just drives up the need for this added hardware. It adds to the stress in the supply chain because these same suppliers now have to source multiple probe cards. And what's even more interesting is that all of these are now complex technologies, micro bump pitch, so they are more expensive. They're complicated probe cards that put additional stress and additional cost in the collateral space. Individual die might be packaged into what we call debug packages for easier failure analysis or debug. Once you integrate die, we all know that visibility, observability decreases unless you invest in a lot of DFT and observability techniques. So one of the ways that is mitigated is by packaging individual die into a standalone debug package for failure analysis. Now, this puts another burden, another aspect of test cost that's not normally considered. So we have additional substrates, additional packages that need to be designed and manufactured, new collaterals because these are different form factors typically than the final product. So all of this drives additional cost in the test space that needs to be accounted for. Again, disaggregation keeps driving the need for dense interconnect as heterogeneous integration increases. The more amount of die we put on a package, the more dense the interconnect becomes because the connectivity between IP that just keeps increasing. And again, this drives up very aggressive pitch reduction, very high density microbumps, and very dense die-to-die interconnect. So all of these add a lot of complexity to our probe card technology. And this is further exacerbated when we go into more advanced packaging techniques and more advanced disaggregation techniques such as 3D bonding, hybrid bonding, excuse me. So in addition to all of these hardware vectors, hardware cost extenders, we also drive a lot of test overhead and test complexity. Some of it is rather basic. We have multiple chiplets. Each of them will need your basic connectivity, basic opens and shorts testing, contact resistance. Standard things that you would do once are now split across multiple die. So you pay for this added overhead in test time. Typically, we've been able to mitigate these kinds of increases in our product costs by using wafer parallelism techniques, test parallelism. It's pretty standard what the industry has done on this. We just increase the number of sites we test on. However, that comes at there's a trade-off involved. Test parallelism needs us to reduce probe counts, so that we can fit more die in the same test hardware space, or we increase our tester channel count. Either of these is a trade-off, comes with cost. You driving probe count down reduces connectivity and limits wafer test. It diverges from what you would be doing in final test because you just don't have that connectivity, and drives differences in test methods. Or increasing tester channel count increases test hardware costs. So again, it's trade-off that needs to be made, which is appropriate based on the product decisions, product testability requirements. We talked about tight pitch microbumps on disaggregated die because of the die-to-die interconnect. This poses signal integrity challenges for all of our high-speed IOs. A lot of this can be mitigated with extended DFT, loop back technologies at the wafer sort space. But this drives, again, divergence with package test, with final test. You're maybe doing, you're limited by the frequencies you can test. You're limited by the data rates because of the signal integrity issues. And so you may not match what you would need to do in final package test. And that causes potential yield loss downstream in your final test socket. and again, is a cost adder, complexity adder for disaggregated products. So many different trade-offs need to be considered here between cost and complexity across the test space. So then let's talk about something more interesting. In addition to all of these complexities just in wafer test, we also now have yet another vector with the test of the interposer itself, or the base die. And again, disaggregation drives the usage of this base die, this substrate for either the die-to-die connections between the die or die-to-package connections. And we have to consider test strategies for these base die. Do we test them? What are the different upsides or downsides of testing base die? There's a few issues. These interposers are typically built on lower process technologies, lower cost process technologies, and yet we might say, okay, they might be really high yield, so we might just blind build and rely on low defect densities for this particular silicon interposer technology and not test it. The risk is we might take package fallout, and again, then that's a very costly loss because you're losing all of the integrated die on this base die if that happens, because there's a defect in the interconnect. We can incorporate test and redundancy techniques. There can be redundancy built in. There can be recovery built in, lane repair built in. All of these things require DFX changes on your top die, require some level of standardization. I think this has been mentioned in some of the previous presentations. And all of these techniques need to be incorporated and have a impact in terms of test complexity, test times, on how much you want to do, how many repairs you want to find, how do we do that repair, how do we propagate that to all of our next test steps. Or we can do sampling strategies where a certain portion of the die are tested, certain portion of the base wafers are tested, and based on that, you decide your yield for the base die. So again, many different techniques can be applied, but the key message is base die testing is now adding a new dimension to our test economics in this disaggregated future. This is not something that we considered as much in the past. So then let's talk about known good die, and let's talk about another new paradigm that's coming up, stack die testing. As these die keep growing, as the number of chiplets in the die stack grows, yield reduces. Even if we're at 99% yield for each chiplet, the overall package yield would be quite low. This is a direct impact to our product cost, and this then drives a much higher need for a well-established wafer sort condition. You want to drive your yields higher and higher and higher at the chiplet level, so that your package yield loss, final test yield loss, system level yield loss, SLT yield loss is reduced. So this known good die poses an interesting problem. Die-to-die interfaces cannot be fully tested in the sort space. You just don't have that connectivity. The diagram here indicates that you can access the one side of the interconnect in your dielet or in your chiplet, but the actual interconnect and the actual connection between the two die can only be accessed once the stack is assembled. It's not exposed to the package. These are pure die-to-die connections through the substrate, through the base die, and you can only get to them once the die are put together on the stack. So to drive yields to drive yields higher in package test, you probably want to introduce the stack die testing of the stack once the stack is assembled before actual package assembly. this allows us to save cost on substrate. But again, it's a trade-off between package test versus stack die test cost. Again, we talked about this, but redundancy and repair of interconnect needs to be added to this stack die test step, and additional DFX and die area complexity and test complexity gets introduced by this. So this is, again, a new paradigm. Stack die testing is something that, depending on the cost and complexity and economics of the product cost overall, might make sense. But again, this drives up the cost as compared to a monolithic baseline where this was not factored in at all. Okay. Then let's talk about characterized KGD, or characterized known good die. So one of the interesting aspects of known good die and die disaggregation is, how do we pair them? How do we pair different chiplets when we go to package? Do we just randomize it? Or do we have a very specific strategy to pair different types of die with different performance levels before stacking, so that we get the right performance and right power characteristics of the final product? And we typically would want to pair high performance die together. We might want to have a mix of high performance for some of the dielets and medium performance for some of the other dielets. It might depend on how the product is architected, but there needs to be sort of an intelligent pairing of die, so that we can squeeze out optimal power and frequency performance. If we don't do that, we have a risk of either higher yield loss or loss of performance in the final package. So to achieve this, however, we need a more robust wafer sort strategy at the die level. You need to be able to characterize frequency and power and other characteristics of this die before they even hit final test. The issues here are, there's power delivery differences at wafer sort that might cause a difference between a final package versus just bare die testing. There's differences in test content. Again, connectivity might drive differences in how you test. So a lot of these items drive differences and add complexity. So the more we want to characterize, the more test time and test complexity it takes at the wafer sort socket, and drives up our test cost. The chart below indicates sort of this concept of populations of chiplets. The more subpopulations we divide disaggregated die, the better pairing we can get, and we reduce our chiplet to chiplet variation and are able to do intelligent pairing. The chart on the right hand side indicates a monolithic die has much lower variation within the die, but in a disaggregated environment with smaller chiplets, chiplet to chiplet variation is higher. So you would want to do a much better job of characterizing and pairing and creating subpopulations of like die to create these groups and be able to pair die intelligently. And again, that drives a test time at sort, that drives additional test content, additional test methods, and all of these things impact test cost. So this is one of these concepts that need to be explored. A lot of work needs to be put in. It's not trivial. It drives up hardware cost, it drives up connectivity cost, it drives up test time. So lots of factors to be considered for characterized known good die. All right, and I think with that, I will end with my last slide here with a summary and call to action. Again, die disaggregation is causing test cost to rapidly approach or cross per transistor cost, which is a problem, because you never want to be in the space of test being more expensive than the actual design. We've seen how disaggregation is causing a lot of complexity in our test space, a lot of cost increase in our test space. characterized known good die is a concept that we need to think about more and more, and that is going to continue to add complexity in our environment. Our hardware costs are going up with more and more advanced packaging techniques and tighter and tighter pitch. Overall, probe card technology and capital costs are just rising exponentially. We've talked about silicon interposer or base die testing, which is now yet another test cost adder, depending on what methodology is used for that. And then we've talked about stack die insertions, which are possibly needed to fully test our die-to-die interconnect, which is yet another new socket, new test cost that's added to our product test cost. In addition to all of this, as packaging technologies advance, and as we go further and further into more complex technologies such as hybrid bonding, that further just adds and exacerbates test complexity. Hybrid bonding is one of these technologies that you don't even have the full stack available. So there's processing steps after the stack is assembled. So is wafer test even a true representation? Or how do you deal with that complexity? And how do you deal with the fact that these pads that are being probed are so small that even probing them causes defects? So there's a lot of these things that need to be considered as these technologies advance. And we need to really think about what the issues with test will be, what the issues will be that will drive up test cost and test complexity. So call to action. Again, I think this is the theme this morning. We need stronger collaboration between our design, packaging, and test partners to ensure that we have optimized test solutions, optimized cost for manufacturing, because a lot of this is not in the forefront when these kinds of architectures are put together. Drive for standards across the industry is great because, again, there are a lot of new vectors are coming up in the test space because of this. And with that, I will end. Just putting some references out and acknowledgement to some of the presenters and some folks that have presented here before, and just a legal notice. Thank you.
Thank you, Samir. Would you mind going back to your conclusion slide for just?
Yes, okay. Sure.
So I'll call it famous or infamous. About 25 years ago, there was a slide from Intel that showed the cost to test a transistor had crossed or was about to cross the cost to manufacture that transistor. Are you suggesting, or does your data show that that is close to happening or has happened again?
I would say it's certainly close to happening. I think we continue to innovate to make sure we don't cross that. But that's what puts a lot of the stress in this system and in the test space, because all of these challenges from disaggregation are driving up our test cost, and they're driving it up exponentially with all of these new challenges, new sockets, the hardware, as I already mentioned. So yes, certainly we are fast approaching it, and we continue to be pressured to make sure we stay behind that cost curve. And there's a lot of effort and resource that needs to be put in to make sure that we don't cross it and exceed it, because then that really challenges the product cost and product economics.
But this time with the heterogeneous integration enabling functionality that's not being achievable through, let's say, Dennard scaling by putting more technology in advanced packaging, could there be a scenario where that would be acceptable, where the test cost was higher than the transistor cost because really the advanced packaging is being used to enable functionality you simply can't get with monolithic die?
Yeah, I think that's a good question, and I think it will really depend on what is the end product case, and if really that product isn't feasible without that kind of advanced packaging, then that case might have to be made. In the end, though, I think test cost is always going to continue to be challenged because in the grand scheme of product cost, everyone wants test cost to be on the low end of the scale, in terms of just the drive for competitiveness and test economics, product economics.
Fully understand. So one of the questions from the audience is, with the economics, so is the economics of chiplets still compelling given the test complexity?
I think it is. I think in general, because overall, as we get into more and more chiplets, overall product yield can be driven up, can be we can switch to more newer process technologies, denser process technologies to eke out performance. I think there's still the efficiency to be gained out of that. There's still product innovation that's gained out of that. It just comes at the price of challenging us in the test world to continue to innovate and make sure that test stays out of the way. So I think we want to be able to support and maintain this innovation with heterogeneous integration. We just need to make sure that test continues to innovate and not be the limiter.
A good point. So there's a few questions, and this a lot of them has to do with micro bumps and pad pitch. So if you could answer some of these that you're comfortable with. Looking at the hybrid bonding or the micro bumps, the question is, how much does testing influence the yield? And I suspect the person is asking or is concerned about the damage to the micro bumps when you contact that. Is there anything you can share from your experience about that? I know Will's going to talk about this in specific tomorrow, but obviously you've looked at this pretty carefully, I believe.
Yeah, maybe I will provide a general answer. I think that's certainly a concern. In terms of does probing itself cause issues with microbumps? I think that's more and more of a concern as we move into more complex stacking techniques such as hybrid bonding. Less so with the current technologies that we have, but overall, the issues that we see are more in the signal integrity space. As we get more and more dense, we might not be able to test all of the bumps, excuse me, all of the bumps on the wafer, and you might have to invest in technologies which don't necessarily contact all the bumps at the same time. But again, that comes with the trade-off that you're now not able to test everything. You might have to reduce your probe count. So different complexities, different trade-offs that occur in that space because of that.
And related to that, I mean, you can't always test, well, if you have a failure to bond a certain number of signals or grounds on microbumps or hybrid bonding, you may not see that at test, but you might have signal integrity issues. Are there methodologies for detecting those?
Yeah, so I think those will be places where stack die testing would come into play. And if you don't rely on stack die testing, then you would probably find those issues either in your final test or in your SLT sockets. So this is why, adding an SLT step helps. Adding a stack die test socket helps because you can find those issues earlier than before you package. Ultimately, some of that you have to make sure that you're able to drive up testability, whether that's engaging with design earlier to make sure that these interfaces are testable, these interconnects are testable, and get these standards in, get the connectivity and observability that you need. But there's always this limitation with wafer sort that you're going to have, and then you're going to have to see if your test methods will be reliable at either stack die or final test.
Understood. And earlier in the presentation, you talked about testing the base die or the silicon interpose or the bridges. Is automated optical inspection sufficient for those, or will those require electrical, or do they require electrical test?
I'm not sure I would be able to answer that very well. It's certainly an option. Again, those would be one of those choices that would need to be made, whether it's blind test, optical test, actual electrical test, and it probably depends on the product application and the type of interconnect that's being used. And so all of those would probably want to be considered in terms of complexity, cost, and impact to product.
Okay, good. And I think this last question well, I'll ask you this, and I think it's something we'll probably address tomorrow, but is there, is it foreseen that there's a particular microbump pitch that is too small to actually probe? And, where do you think the frontier is to do that reliably today? And is there an alternative once you can't do that?
Yeah, I don't know that I'd be well equipped to answer that question, but I think we are approaching that space with the hybrid bonding technologies that are coming up. But it's probably best addressed by somebody that's more of an expert in that field.
Okay. Thank you.
Thank you.
Let's see. I think that is all the questions. I want to thank you for an excellent presentation. And once again, I'd like to thank the sponsors, our diamond sponsor, Amcor, with differentiators in technology, quality, and service. And our Emerald sponsor, Advantest, receiving the highest ratings for customer satisfaction from the VLSI survey for 2 consecutive years. I would like to thank both of them for sponsoring today's event and tomorrow's event, and sponsoring the Road Chiplets series. And with that, I will wish everybody a good day and look forward to having you join us again tomorrow. Thank you.